as you sit here watching this video, 4 invisible forces are doing something extraordinary. They are holding every single atom in your body together. They are keeping the ground beneath your feet solid. They are making the sun burn. They are preventing the galaxies from flying apart. 4 forces. That is all it takes to run the entire universe. Every explosion, every heartbeat, every beam of light, every nuclear reaction inside a star, every chemical bond in your DNA. All of it comes down to 4 fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These 4 forces are the operating system of reality. They are the deepest rules we have ever discovered. And for decades, physicists believed that was the complete list. 4 forces. Nothing more, nothing less. Case closed. But what if that list is wrong? What if there is a 5th one? Now, before you think this is just science fiction or some wild internet theory, let me tell you something. Right now, in laboratories scattered across the world, from a modest research institute in Hungary to the colossal underground tunnels of CERN in Switzerland, from a particle accelerator in Italy to NASA's Jet Propulsion Laboratory in California, real physicists, serious scientists, people who have spent their entire careers being cautious and skeptical, are chasing what might be the most important discovery in modern physics. They are hunting for a 5th fundamental force of nature. And the evidence, while still incomplete, while still debated, while still uncertain, is genuinely fascinating. Strange signals have appeared in nuclear experiments. Particles are behaving in ways that the standard model of physics cannot fully explain. Measurements of the universe on the largest scales do not match what we see in our own solar system. And a mysterious particle, one that nobody predicted, keeps showing up in experiment after experiment, refusing to go away. In today's video, we are going to take a complete journey through this story. And I mean complete. We are going to start from the very beginning. We are going to build a deep understanding of what the 4 known forces are, how they were discovered, and why they are called fundamental. Then we are going to explore the cracks, the problems, the mysteries that tell us something might be missing from our picture of reality. We will dive into the strange experiment in Hungary that reignited this entire search. The mysterious particle called X-17, and every major experiment around the world that is currently racing to confirm or deny its existence. We will explore the theoretical models that physicists have proposed. We will examine the skepticism, because real science demands that we look at both sides honestly. And finally, we will explore what it would mean for humanity if this 5th force turns out to be real. This is going to be a long one. This is going to be a deep one. And I promise you, by the end, your understanding of the universe will be fundamentally different from what it is right now. So if you are the kind of person who genuinely loves understanding how reality works at the deepest level, do me a favor. Hit that subscribe button, press like, and drop a comment telling me what you think. Because content like this takes an enormous amount of research, and your support is what makes it possible. Now, let us begin. To understand why physicists think there might be a 5th fundamental force, we first need to understand what a fundamental force actually is. And this is where most people get confused. Because we use the word force in everyday language all the time. You push a door. That is a force. Wind blows against your face. That is a force. A car engine moves the wheels. That is a force. But none of these are fundamental forces. They are all consequences of the fundamental forces. When you push a door, The force you feel is actually the electromagnetic force, because the atoms in your hand are repelling the atoms in the door through electromagnetic interactions between their electron clouds. When wind blows, that is billions of air molecules bouncing off your skin. Again, through electromagnetic repulsion at the atomic level. Every single force you have ever experienced in your daily life, every push, every pull, every friction, every tension, every pressure, all of it is just electromagnetism in disguise. That is how fundamental these forces are. They are the bedrock. They are the forces from which all other forces emerge. A fundamental force has very specific properties. First, it cannot be broken down into anything simpler. You cannot explain gravity in terms of some other force. Gravity is gravity. It is irreducible. Second, a fundamental force operates through a specific mechanism. In modern physics, we understand that forces work by exchanging particles. Two objects interact because they throw particles back and forth between each other, like two ice skaters passing a ball. These particles are called force carriers, or gauge bosons. Each fundamental force has its own specific carrier particle. Third, a fundamental force has a specific range and strength. Some forces reach across the entire universe, others barely extend beyond the nucleus of an atom. Now, let us walk through the four forces we know, because understanding them deeply is essential for understanding why a fifth one might exist. The first and most familiar force is gravity. Every human being on Earth has an intuitive sense of gravity. You drop something, it falls. You jump, you come back down. The moon orbits the Earth. The Earth orbits the sun. Gravity seems simple and obvious, but it is actually the most mysterious of all four forces, and understanding its history reveals just how strange it really is. For most of human history, people did not think of gravity as a force at all. Things fell because that was their natural tendency. Aristotle, the ancient Greek philosopher, believed that heavy objects fell faster than light objects, and that everything had a natural place it was trying to reach. This was wrong, but it was the accepted wisdom for nearly 2,000 years. Then came Galileo Galilei in the late 1500s. Galileo did something revolutionary. He actually tested the idea. He rolled balls down inclined planes. He timed their descent. And he discovered that all objects fall at the same rate regardless of their mass, once you remove air resistance. This was shocking. A cannonball and a feather in a vacuum hit the ground at exactly the same time. But the person who truly transformed our understanding of gravity was Isaac Newton. In 1687, Newton published his masterwork, the Principia Mathematica, and in it he proposed something that was almost inconceivable at the time. He said that the same force that makes an apple fall from a tree is the same force that keeps the moon in orbit around the Earth, the same force that holds the planets in their paths around the sun. He called it universal gravitation. Every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. This was the first time anyone had proposed a truly universal law of nature, one equation that described the falling of an apple and the motion of the planets with equal precision. Newton's theory of gravity was spectacularly successful. It explained the orbits of the planets. It predicted the existence of Neptune before anyone had ever seen it. It allowed engineers to calculate trajectories for cannonballs and eventually for rockets. For over 200 years, Newtonian gravity was considered essentially perfect. But there was one problem. Newton himself admitted that he had no idea how gravity actually worked. How does the Earth reach out across empty space and pull on the moon? There is no rope. There is no physical connection. Newton called this action at a distance, and he confessed that he found it philosophically unsatisfying. He described what gravity does, but not how it does it. It took another genius to answer that question. Albert Einstein, in 1915, published his general theory of relativity, and it completely revolutionized our understanding of gravity. Einstein proposed that gravity is not a force at all, at least not in the traditional sense. Instead, massive objects curve the fabric of space-time itself. Imagine placing a heavy bowling ball on a stretched rubber sheet. The ball creates a dip, a curve in the sheet. Now, roll a marble nearby. The marble does not fall toward the bowling ball because of some invisible pull. It falls because the surface it is rolling on is curved. The marble is just following the natural path through curved space. That is gravity. The Earth does not pull you down. The Earth curves space-time around it, and you follow that curve. Einstein's theory made predictions that Newton's could not. It predicted that light itself should bend when passing near a massive object, which was confirmed during a solar eclipse in 1919. It predicted that time runs slower in stronger gravitational fields, which has been confirmed with atomic clocks on airplanes and satellites. Your GPS system would not work without corrections for this effect. It predicted gravitational waves, ripples in space-time caused by accelerating massive objects, which were finally detected in 2015 by LIGO, exactly 100 years after Einstein predicted them. But here is the deep mystery about gravity. Despite all of this success, gravity is the only fundamental force that we have not been able to incorporate into the framework of quantum mechanics. The other three forces all have a quantum description. They all have well-defined force carrier particles. Gravity is supposed to be carried by a particle called the graviton, but no one has ever detected one. In fact, we do not even have a consistent mathematical theory of quantum gravity. When you try to apply quantum mechanics to gravity, the equations produce infinities. They break down. They give nonsensical answers. This is one of the biggest unsolved problems in all of physics, and it is one of the reasons physicists suspect there might be more to the story than we currently understand. There is another remarkable thing about gravity. It is incredibly, almost absurdly, weak compared to the other forces. How weak? Here is an illustration. Take a small refrigerator magnet. That tiny magnet, just a few grams of material, can stick to a refrigerator and hold itself there against the gravitational pull of the entire planet Earth. The electromagnetic force in that tiny magnet is defeating the gravity of 6 trillion kilograms of rock and iron. Gravity is about 10 to the power of 38 times weaker than the strong nuclear force. That is a 1 followed by 38 zeros. Why is gravity so incredibly weak? Nobody knows. This is called the hierarchy problem, and as we will see later, it is one of the motivations for thinking a fifth force might exist. The second fundamental force is electromagnetism. This is the force responsible for almost everything you experience in daily life. The light coming from your screen right now, that is electromagnetism. The reason you do not fall through your chair, electromagnetism, the chemical bonds holding the molecules in your body together. Electromagnetism, your nervous system sending signals from your brain to your fingers. Electromagnetism, radio waves, microwaves, X-rays, all of technology, computers, phones, the internet, electric motors, generators, lasers, all of it is electromagnetism in action. The story of electromagnetism is one of the great triumphs of physics. For a long time, electricity and magnetism were thought to be completely separate phenomena. Electricity was about charged particles attracting and repelling each other. Magnetism was about certain materials pointing north and south. They seemed unrelated. But in the early 1800s, a series of discoveries began to reveal a deep connection. Hans Christian Ørsted discovered that an electric current creates a magnetic field. Michael Faraday discovered that a changing magnetic field creates an electric current. And then came James Clerk Maxwell, who in the 1860s unified everything into a single, beautiful set of equations. Maxwell's equations showed that electricity and magnetism are not two separate forces. They are two aspects of a single force, electromagnetism, and from those equations, Maxwell derived something extraordinary. He showed that electromagnetic waves exist, that they travel at the speed of light, and that light itself is an electromagnetic wave. That was one of the most stunning unifications in the history of science. Two seemingly different phenomena revealed to be manifestations of a single deeper reality. The force carrier of electromagnetism is the photon. Photons are massless particles that travel at the speed of light. Because they are massless, the electromagnetic force has infinite range. A photon can travel from a galaxy billions of light-years away and still reach your eye. That is why we can see distant stars and galaxies. But unlike gravity, electromagnetism can both attract and repel. Positive charges attract negative charges, like charges repel each other. This means that while electromagnetism is much stronger than gravity, it tends to cancel itself out on large scales. Most large objects are electrically neutral, with equal amounts of positive and negative charge. So gravity, despite being absurdly weak, dominates at the scale of planets, stars, and galaxies, simply because it only attracts and never repels. The third fundamental force is the strong nuclear force, and it is the most powerful force in all of nature. But unless you are a nuclear physicist, you have probably never directly experienced it, because it operates at an almost unimaginably small scale. The strong force holds the nucleus of every atom together, and that is no small task. Think about what a nucleus actually is. It is a collection of protons and neutrons crammed together in an incredibly tiny space, roughly 1 femtometer across, which is a millionth of a billionth of a meter. Now, protons are positively charged, and we just discussed that charges repel each other through the electromagnetic force. So every proton in a nucleus is electromagnetically repelling every other proton with tremendous force. By all rights, every atomic nucleus should instantly blow itself apart. But it does not. Something is holding those protons together despite their electromagnetic repulsion. That something is the strong nuclear force. It is about 100 times stronger than electromagnetism at nuclear distances, which is why it can overcome the electromagnetic repulsion and keep nuclei stable. At a deeper level, the strong force operates between quarks, which are the building blocks of protons and neutrons. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 1 up quark and 2 down quarks. The strong force binds these quarks together through a property called color charge, which is analogous to electric charge but more complex. While electric charge comes in 2 types, positive and negative, color charge comes in 3 types, whimsically named red, green, and blue. The force carrier particles of the strong force are called gluons, and unlike photons, gluons themselves carry color charge. This means gluons interact with each other, not just with quarks. This self-interaction gives the strong force a bizarre property called confinement. You can never isolate a single quark. If you try to pull two quarks apart, the energy stored in the gluon field between them eventually becomes so great that it creates a new quark-antiquark pair. So instead of getting a free quark, you just get more particles. Quarks are permanently imprisoned inside protons, neutrons, and other composite particles called hadrons. The strong force has an extremely short range, about 1 femtometer. Beyond that distance, it drops to essentially zero. This is why the strong force does not affect everyday objects. It is confined to the interior of atomic nuclei. But within that tiny domain, it is king. Without the strong force, no atomic nucleus heavier than hydrogen could exist. No carbon, no oxygen, no iron. No chemistry. No stars, because nuclear fusion in stars relies on the strong force to bind protons and neutrons together into new elements. Without the strong force, the universe would contain nothing but a dilute gas of hydrogen and isolated protons. No complexity. No life. Nothing. The fourth and final known fundamental force is the weak nuclear force, and it is perhaps the most subtle and least intuitive of the four. The weak force is responsible for certain types of radioactive decay, most notably beta decay, in which a neutron transforms into a proton by emitting an electron and an antineutrino. This might sound like a minor process, but it is absolutely essential for the existence of the universe as we know it. The weak force is carried by three particles: the W+ boson, the W- boson, and the Z boson. Unlike photons and gluons, these particles are extremely massive. The W bosons have a mass about 80 times the mass of a proton, and the Z boson is about 91 times the mass of a proton. Because these carrier particles are so heavy, the weak force has an incredibly short range, much shorter even than the strong force. It operates at distances of about 0.001 femtometers, roughly 1,000th the size of a proton. This extreme short range is why it is called the weak force. It is not that the force itself is inherently feeble. At very short distances, it is comparable in strength to electromagnetism. But because its range is so tiny, its effects are rarely felt. But do not be fooled by the name weak. This force does something that no other force can do. It changes the identity of particles. The strong force can shuffle quarks around, but it cannot change one type of quark into another. Electromagnetism does not change particle types at all. Gravity certainly does not. But the weak force can turn an up quark into a down quark, thereby converting a proton into a neutron, or vice versa. This is the only force in nature that can do this, and it has profound consequences. Without the weak force, nuclear fusion in the Sun would not work. The very first step of the proton-proton chain, which powers our Sun, requires the weak force to convert a proton into a neutron. Without this step, the Sun could not fuse hydrogen into helium. It would not shine. No star in the universe would burn through this process. Furthermore, the weak force played a critical role in the early universe. In the first few minutes after the Big Bang, the weak force determined the ratio of protons to neutrons, which in turn determined how much hydrogen and helium the universe would contain. Change the strength of the weak force, and you change the chemistry of the entire universe. There is another remarkable property of the weak force that makes it unique among all four forces. It violates a symmetry called parity. Parity symmetry says that the laws of physics should be the same if you look at them in a mirror. For gravity, electromagnetism, and the strong force, this is true. The mirror image of any process involving these forces is equally valid. But the weak force breaks this rule. It treats left and right differently. Specifically, the weak force only interacts with left-handed particles and right-handed antiparticles. If you could somehow flip a neutrino to make it right-handed, the weak force would completely ignore it. This is deeply strange. Why would one of the fundamental forces care about chirality, about the handedness of particles? Nobody has a fully satisfying explanation. It is one of the deep mysteries of the Standard Model. There is one more beautiful piece of this story that needs to be told before we move on. In the 1960s and 70s, three physicists, Sheldon Glashow, Abdus Salam, and Steven Weinberg, made a stunning theoretical breakthrough. They showed that electromagnetism and the weak nuclear force are actually the same force, disguised. At very high energies, above about 100 billion electron volts, the electromagnetic force and the weak force merge into a single unified force called the electroweak force. This unification only becomes apparent at extreme energies, like those that existed in the very early universe. At everyday energies, the forces look completely different because the W and Z bosons are massive, while the photon is massless. And this mass difference is created by the Higgs field, which gives mass to the W and Z bosons, but not to the photon. This electroweak unification earned Glashow, Salam, and Weinberg the Nobel Prize. And it set the stage for one of the grandest ambitions in all of physics. If electromagnetism and the weak force are secretly the same force at high enough energy, could the same be true for all four forces? Could there be a single, unified force from which all four emerge? Grand unified theories attempt to merge the strong force with the electro-weak force at even higher energies. And the ultimate dream, a theory of everything, would incorporate gravity as well. In this vision, at the unimaginable temperatures of the very first moments of the Big Bang, there was only one force. As the universe cooled, this single force split into gravity first, then the strong force separated, and finally, electromagnetism and the weak force went their separate ways. Four forces, all born from a single parent. This is a beautiful vision. But it is incomplete, and the incompleteness is not a minor detail. There are gaping holes in our understanding, problems so fundamental that they suggest our picture of reality might be deeply, profoundly wrong. And these holes are exactly where the fifth force might be hiding. Let us now explore those holes, because this is where the story gets really interesting. The first and perhaps most dramatic problem is dark matter. This is not some minor theoretical curiosity. This is the discovery that most of the matter in the universe is invisible. We cannot see it. We cannot touch it. We cannot detect it with any instrument we have ever built. But we know it is there, because its gravity shapes the visible universe in ways that are impossible to explain without it. The story begins in 1933, when a Swiss-American astronomer named Fritz Zwicky was studying the Coma Cluster, a large cluster of galaxies about 320 million light-years from Earth. Zwicky measured the velocities of the galaxies in the cluster. He used these velocities, along with the gravitational equations, to calculate how much mass the cluster must contain to hold itself together. Then he compared this to the mass he could actually see, the visible galaxies and gas, and the numbers did not match. The visible mass was far too small. The galaxies were moving so fast that the cluster should have flown apart long ago. Something invisible was providing extra gravitational pull. Zwicky called this missing component dark matter. His discovery was largely ignored for decades. But in the 1970s, astronomer Vera Rubin made observations that were impossible to dismiss. Rubin studied the rotation curves of galaxies, meaning she measured how fast different parts of a galaxy were rotating around its center. According to Newton's and Einstein's equations, the outer regions of a galaxy, far from most of the visible mass, should orbit more slowly, just as the outer planets in our solar system orbit more slowly than the inner ones. But Rubin found something bizarre. The outer regions of galaxies were orbiting just as fast as the inner regions. The rotation curves were flat. This meant that there was far more mass in the outer regions of galaxies than could be accounted for by visible matter. The galaxies were embedded in enormous halos of invisible matter, dark matter, extending far beyond the visible edges of the galaxies. Since then, the evidence for dark matter has only grown stronger and more diverse. Gravitational lensing, where the gravity of invisible mass bends the light from distant galaxies, provides a direct map of dark matter distribution. The cosmic microwave background, the afterglow of the Big Bang, shows patterns that are perfectly explained by the presence of dark matter in the early universe. Computer simulations of cosmic structure formation reproduce the observed distribution of galaxies only when dark matter is included. Remove dark matter from the simulations, and the universe looks nothing like what we observe. And the numbers are staggering. Roughly 27% of the total energy content of the universe is dark matter. Only about 5% is ordinary matter, the atoms that make up stars, planets, and people. We, and everything we can see and touch, are the minority. The universe is mostly made of something else. And here is the deeply troubling part. Dark matter does not interact through electromagnetism. It does not emit light, absorb light, or reflect light. That is why it is dark. It does not interact through the strong nuclear force. It is not made of quarks or gluons. As far as we can tell, the only known force dark matter responds to is gravity. But even that is not entirely satisfying, because we have no idea what dark matter actually is at the particle level. Dozens of experiments around the world have spent decades trying to detect dark matter particles directly. Enormous detectors buried deep underground, shielded from cosmic rays, waiting for a dark matter particle to bump into an atom of xenon or germanium. So far, nothing. Zero confirmed detections. This raises an obvious question. If dark matter interacts through gravity but nothing else, why is it so hard to detect? But what if that assumption is wrong? What if dark matter does interact through a force, just not one of the four we know? What if there is a fifth force, one that connects the visible world to the dark world? A force so feeble, so subtle, that it has escaped detection until now. This is one of the primary motivations driving the search for a fifth fundamental force. The second great mystery is dark energy, and it makes the dark matter problem look simple by comparison. In 1998, two independent teams of astronomers were studying distant supernovae, Type 1a supernovae, which are used as standard candles because they all explode with roughly the same brightness. By measuring how bright a supernova appears and comparing it to how bright it actually is, you can calculate how far away it is. And by measuring the redshift of its light, you can determine how fast it is moving away from us. The teams expected to find that the expansion of the universe was slowing down. After all, gravity pulls everything together, so the expansion should be decelerating. like a ball thrown into the air that gradually slows before falling back down. But that is not what they found. The expansion was not slowing down, it was speeding up. The universe was accelerating in its expansion, as if some mysterious energy were pushing space apart, counteracting gravity on the largest scales. This discovery was so shocking that it won the Nobel Prize in Physics in 2011. The mysterious energy driving this acceleration was named dark energy, and it constitutes approximately 68% of the total energy content of the universe. Let that sink in for a moment. 68% dark energy, 27% dark matter, 5% ordinary matter. We understand 5% of the universe. 95% is a complete mystery. Now, the simplest explanation for dark energy is Einstein's cosmological constant, a uniform energy density permeating all of space. Einstein originally introduced it in his equations to keep the universe static, then abandoned it when the universe was found to be expanding, calling it his greatest blunder. But with the discovery of accelerating expansion, the cosmological constant was resurrected. The problem is, when physicists try to calculate the expected value of the cosmological constant using quantum field theory, they get an answer that is too large by a factor of 10 to the power of 120. That is 1 followed by 120 zeros. This is often called the worst prediction in the history of physics. This enormous discrepancy suggests that something is fundamentally wrong with our understanding. And one possible resolution is that dark energy is not a cosmological constant at all. Instead, it might be a dynamic field, something that changes over time and space. This type of field is often called quintessence, borrowing the term from the ancient Greek concept of a fifth element. And here is where it connects to our story. A dynamic quintessence field would naturally create a new force, a fifth force, that acts on matter and energy in subtle ways. The properties of this force would depend on the specific model, but in many scenarios, it would be incredibly weak and operate primarily on very large scales, which is exactly where dark energy effects are most noticeable. This brings us to a remarkable concept called the Great Disconnect, which was highlighted in a 2026 paper by Slava Turishev, a physicist at NASA's Jet Propulsion Laboratory. Turishev pointed out something deeply puzzling. On cosmic scales, the universe clearly behaves in ways that require dark energy and dark matter to explain. Galaxies rotate too fast. The universe accelerates its expansion. Large-scale structure follows patterns that require invisible components, but within our own solar system, everything is perfectly normal. The planets orbit exactly as Einstein's general relativity predicts. Spacecraft trajectories match calculations with extraordinary precision. There is no sign of dark energy or dark matter effects at the solar system scale. This is the Great Disconnect. The physics of the very large and the physics of the local seem to be operating under different rules. Now, if dark energy was simply a cosmological constant, this disconnect would make perfect sense. A constant energy density would produce effects too small to measure at solar system scales. But if dark energy is actually a fifth force mediated by a scalar field, something different might be happening. The force might be hiding itself in dense environments through a mechanism called screening. We will explore these screening mechanisms in detail later, but the basic idea is extraordinary. Imagine a force that is strong in the emptiness between galaxies, but becomes essentially invisible in the presence of matter. A force that camouflages itself. A force that actively hides from our experiments. If such a thing exists, it would explain the Great Disconnect perfectly. and Turishev's paper argues that, with sufficiently sensitive instruments, we might be able to detect traces of this hidden force right here in our own solar system. The third major problem is the hierarchy problem, which we touched on briefly when discussing gravity. Why is gravity so incredibly weak compared to the other forces? To appreciate just how bizarre this is, consider the following. The electromagnetic force between two electrons is about 10 to the 36th power times stronger than the gravitational force between them. The strong force is even more powerful. For the standard model to produce a universe where gravity is this weak, certain parameters must be fine-tuned to extraordinary precision. It is like balancing a pencil on its tip on a moving train in an earthquake. Technically possible, but so improbable that most physicists believe there must be a deeper explanation. Several proposed explanations involve new forces or dimensions. In string theory and models with extra dimensions, gravity might appear weak because it spreads out into additional spatial dimensions that the other forces cannot access. In other models, new particles and forces exist at energy scales just beyond what our current experiments can reach. If any of these models are correct, new forces would necessarily exist, and they might be detectable. The fourth problem is the matter-antimatter asymmetry. When the Big Bang created the universe, it should have produced exactly equal amounts of matter and antimatter. And when matter and antimatter meet, they annihilate each other completely, converting into pure energy. So if the Big Bang was perfectly symmetric, all the matter and antimatter should have destroyed each other, leaving behind a universe of nothing but photons. Obviously, that did not happen. We are here. Stars are here. Galaxies are here. There is a tiny excess of matter over antimatter, roughly 1 part in a billion, that survived the Great Annihilation and went on to form everything we see. But where did that asymmetry come from? The standard model contains some mechanisms that can produce matter-antimatter asymmetry, specifically CP violation in the weak force. But the amount of asymmetry these mechanisms produce is far too small to explain the observed excess. Something else must be creating the imbalance. And one possibility is a new force that treats matter and antimatter slightly differently. A fifth force with the right properties could tip the balance just enough to explain why there is something rather than nothing. These four problems, dark matter, dark energy, the hierarchy problem, and the matter-antimatter asymmetry, are not minor inconsistencies. They are fundamental failures of our current understanding. They tell us that the standard model, despite being the most successful theory in the history of science, is incomplete. Something is missing. And a fifth force is one of the most compelling candidates for what that missing piece might be. But the search for a fifth force is not new. It has a long and fascinating history, full of false starts, dashed hopes, and hard-won lessons. Let us travel back in time to understand how this hunt began. The story really starts with a Hungarian physicist named Loránd Eötvös, who lived from 1848 to 1919. Eötvös was obsessed with a question that seems almost trivially simple, but is actually one of the most profound in all of physics. Does everything fall at the same rate? We know from Galileo's experiments that a heavy ball and a light ball, dropped from the same height in a vacuum, hit the ground at the same time. But why? In Newton's framework, there are two types of mass. Inertial mass determines how much an object resists acceleration when you push it. Gravitational mass determines how strongly it is pulled by gravity. These are conceptually different things. Inertial mass is about motion. Gravitational mass is about gravity. There is no obvious reason they should be equal. And yet, they are. To extraordinary precision, they are exactly equal. This equality is called the equivalence principle, and Einstein made it the foundation of general relativity. Eötvös built an incredibly sensitive instrument called a torsion balance to test whether the equivalence principle was truly exact. His device could detect differences in gravitational and inertial mass at the level of 1 part in 100 million. He tested various materials and found no violation. The equivalence principle held. But the precision of his measurements was so extraordinary that they became a benchmark for decades. Now, fast forward to 1986. An American physicist named Ephraim Fishbach at Purdue University re-examined Eötvös's century-old data, and he noticed something curious. There appeared to be a slight correlation between the composition of the materials Eötvös tested and the results he obtained. Materials with different ratios of protons to neutrons seemed to show tiny but systematic differences in their gravitational behavior. Fishbach interpreted this as evidence for a new force, one that depended on the composition of matter, not just its mass. He proposed that gravity was slightly modified at short ranges, with an additional Yukawa-type interaction that fell off exponentially with distance. This new force would cause objects with different nuclear compositions to fall at slightly different rates, violating the equivalence principle. Fishbach published his analysis in Physical Review Letters on January 6, 1986, and it sent shockwaves through the physics community. Newspapers around the world proclaimed the discovery of a fifth force. The scientific establishment was both excited and skeptical. If Fishbach was right, it would be one of the most important discoveries in the history of physics. But extraordinary claims require extraordinary evidence. What followed was one of the most intensive experimental campaigns in modern physics. Laboratories around the world scrambled to test Fishbach's prediction. Experiments were conducted in towers, where researchers measured whether objects of different compositions fell at different rates. Experiments were conducted in mine shafts, where the inverse square law of gravity could be tested at different depths. Experiments were conducted on submarines, using the ocean as a gravitational screen. Researchers even drilled boreholes into the Greenland ice sheet to measure gravity at depth. Some early results seemed to support the fifth force hypothesis. An Australian group found a small anomaly in gravitational measurements at a mine site. A group studying the gravitational constant reported discrepancies between measurements made at different locations. But as more data accumulated, the picture changed. Most experiments found no deviation from standard gravity. The Australian anomaly was attributed to local geological variations. The gravitational constant discrepancies were traced to systematic errors in the measurements. By the early 1990s, the consensus had shifted decisively against the fifth force. Even Fishbach himself acknowledged that the evidence was not compelling. The episode is often presented as a failure, but it was actually a triumph of the scientific method. A bold hypothesis was proposed. It was rigorously tested. It was found wanting. The process worked exactly as it should. And crucially, Eötvös's original results were re-examined and found to be consistent with standard physics after all. The apparent composition dependence was a statistical artifact. But the search did not end. Physicists continued refining their experiments, pushing the precision ever higher. In 2022, the Microscope satellite, a French space mission specifically designed to test the equivalence principle in the microgravity environment of orbit, published its final results. Microscope measured the relative acceleration of two different test masses, one made of platinum and one made of titanium, as they orbited the Earth. The satellite found no violation of the equivalence principle at a precision of 1 part in 10 to the 15th power. That is 1,000 times more precise than any previous ground-based experiment. If a fifth force violates the equivalence principle, it must be incredibly weak at the scale microscope was testing. But here is the crucial point. Microscope tested the equivalence principle at a specific range and for specific materials. A fifth force could still exist and be consistent with microscope's null result if it has the right properties. If the force is very short-ranged, microscope would not have detected it. If it has a screening mechanism that suppresses it in dense environments, microscope would not have detected it. The search continues, and the next chapter takes us to a small laboratory in the Hungarian city of Debrecen. This is where the story takes its most dramatic turn. Because in 2015, a team of nuclear physicists at the Atomki Institute for Nuclear Research in Hungary observed something that nobody expected. Something that, if confirmed, would be the first direct evidence of a fifth fundamental force. The team was led by Attila Krasznahorkai, a nuclear physicist who had spent his career studying the internal structure of atomic nuclei. Krasznahorkai was not looking for a fifth force. He was looking for dark photons, which are hypothetical particles that some theories propose as force carriers in the dark sector. To search for them, he designed a clever experiment. His team fired protons at a lithium-7 target. When a proton strikes a lithium-7 nucleus, it can create an excited state of beryllium-8. This excited beryllium-8 nucleus is unstable and quickly decays. One of the ways it can decay is by emitting a virtual photon, which then converts into an electron-positron pair. The electron flies off in one direction. The positron flies off in another direction. And the angle between them depends on the energy of the virtual photon and the dynamics of the decay. Standard nuclear physics provides clear predictions for how these electron-positron pairs should be distributed across different angles. As the angle increases, the number of pairs should decrease smoothly and gradually. This is well understood physics. Thousands of nuclear decay experiments have confirmed this pattern. There should be no bumps, no spikes, no unexpected features. But Krasznahorkai's team saw something anomalous. When they plotted the number of electron-positron pairs as a function of the angle between them, they observed a smooth decrease, as expected at most angles. But at approximately 140 degrees, there was a bump. A clear, statistically significant excess of events. More electron-positron pairs were coming out at this specific angle than the standard model predicted. It was as if something was creating extra pairs. And the most natural explanation for a bump at a specific angle is that a new particle is being produced. Instead of the beryllium-8 nucleus emitting a virtual photon that decays into an electron-positron pair, it was sometimes emitting a new, real particle that then decayed into an electron-positron pair. And based on the angle and energy of the excess events, the mass of this new particle could be calculated. It came out to approximately 17 million electron volts, or 17 mega-electron volts. This is about 33 times the mass of an electron, but still very light compared to protons, which have a mass of about 938 mega-electron volts. Part 2, the Atomki team named this hypothetical particle the X17 boson, and the statistical significance of their result was 6.8 sigma. In particle physics, the gold standard for claiming a discovery is 5 sigma, which corresponds to about a 1 in 3.5 million chance that the signal is a random fluctuation. 6.8 sigma exceeds that threshold considerably. The physics world took notice, but with caution. Nuclear physics experiments are complex. Systematic errors can masquerade as signals. And extraordinary claims from a single experiment, especially from a relatively small and unknown laboratory, naturally invite skepticism. The appropriate response was clear: replicate the experiment, and until then, treat the result as intriguing but unconfirmed. But here is where Krasznahorky did something important. Instead of simply repeating the same experiment, he tested the hypothesis in a completely different nuclear system. If the X-17 particle is real, it should not only appear in beryllium-8 decays, it should appear whenever a nuclear transition produces the right conditions. So the Atomky team set up a new experiment, this time using helium-4. In 2019, the team published their results from the helium-4 experiment. They observed the same anomaly: an excess of electron-positron pairs at an angle consistent with the production and decay of a particle with a mass of approximately 17 megaelectronvolts. The same particle, showing up in a completely different nuclear system. This was significant because many potential systematic errors are specific to a particular experimental setup. If you see the same signal in two completely different experiments using different targets, different nuclear transitions, and different kinematic conditions, it becomes much harder to dismiss as a systematic artifact. The media erupted. Major news outlets around the world covered the story. CNN, BBC, Scientific American, Nature, all reported on the possible discovery of a fifth force of nature. The excitement was real, but so was the caution. Two observations from the same group, however compelling, do not constitute proof. Independent confirmation was essential. The Atomky team continued their work, expanding to yet another nuclear system, carbon-12. In 2022 and 2023, they reported observing the X-17 anomaly in carbon-12 nuclear transitions as well. And they also observed it in what is called the giant dipole resonance decay of beryllium-8, which is a different excitation mode from their original observation. Every new nuclear system that showed the anomaly strengthened the case. But every observation still came from the same laboratory, the same team, the same detector technology. Then, in 2024, something important happened. A research group from VU University of Science in Vietnam reported their results from an independent experiment designed to test the Atomky beryllium-8 observation. They used a completely different detector design, a two-arm electron-positron pair spectrometer, and they confirmed the presence of the anomaly. This was the first significant independent observational support for the Atomky signal from outside Hungary. Now, let us pause here and understand what was actually being claimed, because the implications are enormous. The claim was not just that a new particle exists. The claim was that this new particle is a boson, a force-carrying particle, which would mediate a completely new fundamental interaction. If the X-17 is a gauge boson, a carrier of a new force, then its discovery would mean that the four forces we know are not the complete list. There is a fifth. But what kind of force would the X-17 carry? This is where the theoretical physicists entered the picture, and their analysis proved just as fascinating as the experimental results. In 2016, shortly after the original Atomky result was published, a team of theoretical physicists led by Jonathan Feng at the University of California, Irvine, took a hard look at the data. They asked a simple question. If a new particle with a mass of 17 megaelectronvolts exists, what must its properties be? What constraints do existing experiments already place on it? Because the X-17 did not appear out of nowhere. Physicists have been smashing particles together and studying their decays for decades. If a particle with these properties existed, why had nobody seen it before? The answer Feng and his colleagues arrived at was remarkable. They proposed that the X-17 is what they called a protophobic vector boson. Let me break that down. A vector boson is a force-carrying particle with a spin of 1, similar to the photon, the W and Z bosons, and the gluon. The word protophobic literally means proton-fearing. It means that this particle couples to neutrons and electrons, but it essentially ignores protons. It does not interact with protons, or if it does, the interaction is extremely weak. This protophobic property is the key to understanding why the X-17 could have escaped detection for so long. Most particle physics experiments involve smashing protons together, or colliding electrons with protons, or studying processes dominated by proton interactions. If the X-17 barely interacts with protons, it would be nearly invisible in these experiments. It would only reveal itself in experiments that are specifically sensitive to neutron interactions, like the nuclear transitions studied at Atomki, where the neutron-rich nature of the beryllium-8 and helium-4 nuclei provides the right conditions for X-17 production. Feng's analysis showed that a protophobic vector boson with a mass near 17 megaelectronvolts could be consistent with all existing experimental constraints. It would not contradict any known measurement, and it could explain the Atomki anomaly elegantly. Furthermore, Feng pointed out that such a particle could potentially serve as a portal between visible matter and the dark sector. If the X-17 couples to dark matter particles as well as to neutrons and electrons, it could be the long-sought connection between our world and the invisible 27% of the universe. This was a compelling theoretical framework. But science is not about compelling stories. It is about evidence. And as more experiments were conducted and more data were collected, the theoretical picture became more complex. One issue emerged from the carbon-12 observations. The properties required for the X-17 to explain the carbon-12 anomaly were slightly different from those required to explain the beryllium-8 anomaly if the X-17 was a purely protophobic vector boson. This created tension within the theoretical model. Not a fatal contradiction, but a discomfort. Something was not quite fitting together perfectly. In response, theorists developed more sophisticated models. In 2024 and 2025, several groups proposed that the X-17 might have what are called chiral couplings. Instead of being a purely vector boson, it might interact differently with left-handed and right-handed particles. Similar to how the weak force operates, this chiral model could simultaneously explain the beryllium-8, helium-4, and carbon-12 observations, and it could also satisfy constraints from experiments involving pion decays, which had been problematic for simpler models. There was also an entirely different theoretical interpretation proposed by physicist Chok-Yin Wong. Wong suggested that the X-17 might not be a fundamental particle at all. Instead, it could be a composite state, essentially a kind of electromagnetic meson, a bound state of a quark and an antiquark held together primarily by electromagnetic interactions within the framework of quantum electrodynamics. If Wong is correct, the 17 megaelectron-volt signal is real. But its interpretation is completely different. It would not indicate a fifth force. Instead, it would reveal a new and unexpected aspect of quantum electrodynamics, which would still be a major discovery, but of a different nature. This highlights an important subtlety. Even if the 17 megaelectron-volt signal is confirmed beyond all doubt, that does not automatically mean there is a fifth force. The signal needs to be confirmed. and then its interpretation needs to be established. These are two separate steps, and both are far from complete. Now, let us turn to the global experimental effort, because the fate of the fifth force hypothesis ultimately rests not on theoretical arguments, but on experimental evidence. And right now, a remarkable array of experiments around the world is actively searching for the X-17 and for signs of new forces. One of the most important experiments is Na-64 at CERN. Na-64 operates at CERN's superproton synchrotron, one of the large particle accelerators in the CERN complex. The experiment uses a clever technique. It fires a high-energy beam of electrons at a fixed target and looks for events where more energy disappears than can be accounted for by known processes. If the electron interacts with the target material and produces an X-17 particle, and if that X-17 escapes the detector without being detected, then the event would show up as missing energy. This missing energy signature is a powerful tool because it does not require detecting the X-17 directly. Instead, it searches for the consequences of the X-17 being produced and then escaping. Na-64 has been running for several years and has published multiple results. So far, the experiment has not detected a clear signal, but what it has done is extremely valuable. It has set stringent limits on the properties of the X-17. Specifically, it has narrowed down the range of coupling strengths that the X-17 can have. If the X-17's interaction strength were above a certain threshold, Na-64 would have seen it. The fact that Na-64 has not seen it means the X-17, if it exists, must interact more weakly than that threshold. This is called setting exclusion limits, and it is one of the most important activities in experimental particle physics. Even a null result is informative, because it tells you where the particle cannot be. Another CERN experiment contributing to this search is Na-62. Na-62 was designed to study extremely rare decays of charged kaons, which are particles composed of a strange quark and an up or down quark. Some of these rare decay channels could produce an X-17 particle as an intermediate step. In 2023, Na-62 published results searching for the X-17 in a specific kaon decay mode and found no signal, placing additional constraints on the X-17's properties. These constraints are complementary to those from Na-64 because they probe different interaction channels. Now we come to what is perhaps the most dramatic recent development in the X-17 saga. The MEG-2 experiment at the Paul Scherrer Institute in Switzerland was originally designed to search for lepton flavor violation, specifically the extremely rare decay of a muon into an electron and a photon. This decay is forbidden in the standard model at an observable rate, so detecting it would be a clear sign of new physics. But the MEG-2 team realized that their experimental setup, with some modifications, could also be used to directly replicate the Atomki beryllium-8 experiment. And their setup was in many ways superior to Atomki's, with better detector resolution, better background suppression, and more sophisticated analysis techniques. In June of 2025, the MEG-2 team presented their results at a major physics conference. They had performed the same type of experiment as Atomki, firing protons at a lithium target to produce excited beryllium-8 nuclei and looking for the electron-positron pair anomaly at the characteristic angle. Their result was stark. They found no significant excess of events. Based on their data, they excluded the Atomki observation at 94% confidence level. In other words, their experiment saw no X-17. This was a significant blow to the X-17 hypothesis. Here was an independent experiment with superior instrumentation, specifically designed to test the Atomki claim, and it found nothing. 94% confidence level is strong, though it falls short of the 95% threshold that physicists typically use for exclusion. So there is still a slim margin, but it certainly raised serious questions about whether the Atomki signal is real. However, the story is not that simple. Around the same time, another experiment was reporting results that pointed in a very different direction. The Padme experiment at the Frascati National Laboratories in Italy was specifically designed to search for dark sector particles, including the X-17. Padme uses a unique approach. It fires a beam of positrons at a thin fixed target. When a positron and an electron annihilate, they can produce a photon and potentially a new particle like the X-17. By carefully varying the beam energy and scanning across the mass range where the X-17 is expected, Padme can look for a resonance, a spike in the production rate at the X-17 specific mass. Padme performed what is called a blind analysis, which is considered the gold standard in particle physics. In a blind analysis, the researchers design their entire analysis methodology before looking at the data in the signal region. They lock in their cuts, their background estimates, their statistical methods, everything. Only after all decisions are final do they open the box and look at the data. This procedure prevents conscious or unconscious bias from influencing the result. When Padme opened their box in 2025, they found an intriguing result. There was a moderate excess of events at a mass of approximately 16.9 mega-electron volts, which is close to the expected mass of the X-17. The statistical significance was about 2 standard deviations, which in physics terminology is often described as a hint rather than evidence. A 2 sigma result has roughly a 5% chance of being a random fluctuation. It is not enough to claim a discovery. It is not even enough to claim strong evidence. But it is enough to keep the hunt very much alive. So here we are with a fascinating tension. Meg 2 says they do not see the X-17. Padme says they might see a hint of it. Atomki says they see it clearly in multiple nuclear systems. Vietnam says they see it in beryllium-8. How do we resolve this? The honest answer is that we do not resolve it yet. This is what the frontier of physics actually looks like. It is messy, it is contradictory, it is frustrating, and it is exactly how progress happens. Different experiments have different sensitivities, different systematic uncertainties, different backgrounds. A signal that is clear in one experiment might be below the detection threshold of another. A systematic error in one experiment might produce a false signal that does not appear elsewhere. The scientific process of resolution takes time, patience, and more experiments. In 2026, a group of theorists published a paper attempting to combine all existing experimental results, both positive and negative, into a single statistical analysis. This combined evidence paper used sophisticated statistical methods to ask the question, taking everything together, is the evidence for the X-17 getting stronger or weaker? The answer was nuanced. The combined statistical significance remained above the threshold for interest, but below the threshold for confirmation. The X-17 hypothesis is alive, but not proven. There is another important piece of experimental evidence that we need to discuss, one that approaches the fifth force question from a completely different angle. In 2025, an international collaboration involving researchers from Germany, Switzerland, and Australia published a remarkable study involving calcium isotopes. Their approach was based on something called a King plot, which is a powerful tool for detecting new forces. Here is the basic idea. Different isotopes of the same element have different numbers of neutrons, but the same number of protons. They all have the same atomic number, but different mass numbers. The electron transition frequencies in these isotopes differ slightly because of the different nuclear masses and nuclear charge distributions. In the Standard Model, if you plot the isotope shifts for one electronic transition against the isotope shifts for another electronic transition, the resulting King plot should be a straight line. Any nonlinearity in the King plot, any deviation from a straight line, could indicate the presence of a new force coupling to the electrons and the nucleus. The research team measured the transition frequencies of 5 stable calcium isotopes, calcium-40, 42, 44, 46, and 48, with extraordinary precision. When they constructed the King plot, they found a clear nonlinearity. The data did not fall on a straight line. This deviation could be interpreted as evidence for a new boson, a new force carrier, with a mass somewhere between 10 electron volts and 10 million electron volts. But there is an important caveat. The nonlinearity in a King plot can also be caused by higher-order nuclear structure effects within the Standard Model. The nucleus is not a simple point charge. It has a finite size, a complex internal structure, and its properties change between isotopes in ways that can introduce nonlinearities without any new physics. The research team acknowledged this and attempted to account for these nuclear effects. But the theoretical calculations of nuclear structure are themselves uncertain, which means the interpretation of the nonlinearity remains ambiguous. It could be new physics. It could be nuclear physics. More work is needed to distinguish between these possibilities. Now, I want to tell you about another experiment that captured enormous attention and initially seemed like it might provide the smoking gun for new physics, possibly including a fifth force. This is the muon G-2 experiment at Fermilab, and its story is both thrilling and sobering. The muon is a particle very much like the electron, but about 207 times heavier. Like the electron, the muon has a tiny magnetic moment, which means it behaves like a small bar magnet. When you place a muon in a magnetic field, it precesses, meaning its magnetic axis rotates, like a spinning top that wobbles. The rate of this precession depends on the muon's magnetic moment, which in turn depends on all the particles and forces that interact with the muon. In quantum mechanics, the muon does not just sit there in empty space. It is constantly interacting with a bubbling quantum vacuum filled with virtual particles popping in and out of existence. Virtual photons, virtual electrons, virtual quarks, virtual W and Z bosons, even virtual Higgs bosons, all contribute tiny corrections to the muon's magnetic moment. These corrections can be calculated with extraordinary precision using the Standard Model, and the muon's anomalous magnetic moment, called G-2, is one of the most precisely calculated quantities in all of physics. The idea is simple but powerful. Calculate the muon's G-2 using the Standard Model. Measure it experimentally. Compare. If they disagree, something is contributing to the muon's magnetic moment that is not in the Standard Model. That something could be a new particle, a new force, a fifth force. In the early 2000s, an experiment at Brookhaven National Laboratory measured the muon's G-2 and found a tantalizing discrepancy with the Standard Model prediction. The experimental value was slightly higher than the theoretical value. The discrepancy was about 3.5 sigma, which is not enough to claim a discovery, but is definitely enough to make physicists sit up and take notice. It was like seeing a shadow move in your peripheral vision. Something might be there, or it might be nothing. To resolve the question, a new, more precise experiment was built at Fermilab. The muon G-2 experiment reused the original magnetic storage ring from Brookhaven, which was transported in a spectacular cross-country move from Long Island, New York to Batavia, Illinois. The new experiment was designed to measure G-2 with 4 times the precision of the Brookhaven experiment. The first results were published in 2021, and they confirmed the Brookhaven measurement almost exactly. The discrepancy with the standard model prediction persisted, now at a combined significance of about 4.2 sigma. This was tantalizingly close to the 5 sigma threshold. Excitement in the physics community was palpable. Were we on the verge of discovering new physics? More data followed in 2023, further reducing the experimental uncertainty and maintaining the discrepancy. But then something changed on the theoretical side. The standard model prediction for the muons G-2 relies on calculating the contributions from all known particles and forces. The most difficult part of this calculation involves the hadronic vacuum polarization, which accounts for the effects of virtual quarks and gluons in the quantum vacuum. For years, the standard theoretical prediction relied on a data-driven approach, using measurements of electron-positron annihilation into hadrons to estimate this contribution. However, an alternative method existed: lattice quantum chromodynamics, or lattice QCD. This involves simulating the behavior of quarks and gluons directly on a supercomputer by discretizing spacetime into a grid and numerically solving the equations of the strong force. Lattice QCD calculations of the hadronic vacuum polarization had been improving for years, and by 2024 and 2025, they had reached a level of precision that allowed for a meaningful comparison with the data-driven approach. And the two methods disagreed. The lattice QCD calculation gave a larger value for the hadronic vacuum polarization contribution than the data-driven method. This larger value brought the standard model prediction closer to the experimental measurement, reducing the discrepancy significantly. In June of 2025, Fermilab published the final results of the muon G-2 experiment. The experimental measurement was incredibly precise, the most precise measurement of this quantity ever achieved. The experimental value was fully consistent with all previous Fermilab measurements. But now, when compared to the latest theoretical prediction incorporating the lattice QCD results, the discrepancy had largely evaporated. The experimental value and the latest standard model prediction were in agreement. This was a profound moment. For years, the muon G-2 anomaly had been one of the strongest hints of new physics beyond the standard model. Many theorists had proposed that the discrepancy was caused by a new particle, potentially related to the X-17, or to supersymmetric partners, or to other exotic states. And now, with improved theoretical calculations, the anomaly had essentially disappeared. Not because the experiment was wrong. The experiment was spectacularly precise and consistent. But because the theoretical prediction had shifted. Now, I need to emphasize that this does not completely close the door. There is a genuine tension between the data-driven and lattice QCD approaches to calculating the hadronic vacuum polarization. They cannot both be right. Either the data-driven approach has unaccounted systematic errors, or the lattice QCD calculations have issues that are not yet understood, or there is new physics that affects one method differently from the other. This tension is an active area of research, and resolving it is crucial for understanding whether the muon's magnetic moment truly agrees with the standard model or harbors a subtle hint of new physics. But for the purposes of our story, the muon G-2 result provides a cautionary tale, a signal that looked like evidence for new physics that persisted for over 2 decades. Turned out to be consistent with the standard model once the theoretical predictions were improved. This is a reminder that the search for a fifth force is not just about making better measurements, it is also about making better calculations. Sometimes what looks like new physics is actually old physics that we did not calculate accurately enough. There is yet another approach to searching for the fifth force that takes us from the subatomic world to the vastness of space. NASA's OSIRIS-RX mission, which collected samples from the asteroid Bennu and returned them to Earth, also provided data useful for testing gravity and fifth force models. By precisely tracking Bennu's orbit around the Sun and comparing its trajectory to the predictions of general relativity, scientists could search for deviations that might indicate a new force. The measurements were exquisitely precise, and the result was that Bennu's orbit agreed perfectly with standard gravitational physics. No deviations were found. This might sound like bad news for the fifth force hypothesis, but it is actually informative in a positive sense. The Bennu measurement places specific constraints on how strong a fifth force can be at the scale of the asteroid's orbit. It tells us that if a fifth force exists, it must be weaker than a certain threshold at that particular range. This is another piece of the puzzle, another constraint that any viable fifth force theory must satisfy. Now let us dive deep into the theoretical models that physicists have developed to describe what the fifth force might be. Because the idea of a fifth force is not just a vague notion. It comes in many specific, mathematically detailed forms, each with distinct predictions that can be tested. Understanding these models is crucial for understanding why the search is so complex and so fascinating. The first and simplest model is the dark photon. In the standard model, the electromagnetic force is mediated by the photon, which is associated with a symmetry group called U1. Some extensions of the standard model propose that there is a second U1 symmetry group, associated with a new gauge field and a new force carrier particle. This new particle is called the dark photon because it is similar to the ordinary photon but couples much more weakly to ordinary matter. The dark photon could potentially interact with dark matter particles, providing a force within the dark sector analogous to electromagnetism in the visible sector. The dark photon was initially considered as a candidate for the X-17 because a new boson mediating a new force is exactly what a dark photon would be. However, there is a problem. A dark photon couples to electric charge. This means it would interact with both protons and electrons. But the atomic data suggested that the X-17 interacts with electrons and neutrons, but not with protons. This mismatch led theorists to consider more exotic possibilities. This brings us to the protophobic fifth force model that we discussed earlier, proposed by Jonathan Feng and his colleagues. In this model, the X-17 is not a dark photon, but a new type of gauge boson associated with a previously unknown symmetry. Its coupling to protons is suppressed, either exactly zero or extremely small, while it couples to neutrons and electrons with measurable strength. This protophobic property would explain the atomic observations and the non-detection in proton-dominated experiments. The protophobic model requires very specific values for the coupling constants. The ratio of its coupling to neutrons versus electrons must be tuned to particular values to satisfy all experimental constraints. This fine-tuning is not necessarily a problem. Some fundamental constants in nature are just what they are. But it does make some theorists uncomfortable. In physics, when a model requires precise tuning of parameters to work, it often suggests that a deeper, more natural explanation exists. As more experimental data accumulated, particularly from the carbon-12 observations and from pion decay experiments, purely protophobic vector models faced increasing tension. This led to the development of what are called chiral, or axial vector models. In these models, the X17 is not a simple vector boson like the photon. Instead, it has axial vector couplings, meaning it interacts differently with left-handed and right-handed particles. This is reminiscent of how the weak force operates, which, as we discussed earlier, is the only known force that violates parity symmetry. Chiral models for the X17 can accommodate the data from beryllium-8, helium-4, and carbon-12 simultaneously, while also satisfying constraints from pion decay experiments, electron-positron collider measurements, and other particle physics data. They predict specific patterns that future experiments can test. For instance, they predict that the angular distribution of electron-positron pairs in X17 decays should have a particular dependence on the nuclear spin of the parent state, which can be measured. In 2024, a theoretical group showed that the X17 with chiral couplings could simultaneously explain several puzzles in particle physics: the Atomic anomaly, certain discrepancies in muonic atom measurements called the muonic Lamb shift, and potentially even aspects of the matter-antimatter asymmetry problem. If this is correct, the X17 is not just a curious anomaly in nuclear physics, it is a key piece of a larger puzzle that connects multiple mysteries. But there is also the alternative interpretation we mentioned earlier. Chuk-Yin Wong's proposal that the X17 is not a fundamental boson at all, but rather a KED meson, a composite state of a quark and an antiquark bound by electromagnetic-like forces. In Wong's framework, the 17 mega-electron-volt particle is a natural consequence of confined quantum electrodynamic interactions, not a new fundamental force carrier. If Wong is right, the anomaly is still a real particle, but its implications are very different. Instead of opening the door to a fifth force, it would reveal a new and unexpected phenomenon within existing physics. This interpretation is controversial and not widely accepted, but it has not been definitively ruled out. Now, let us move into a truly fascinating area of theoretical physics that connects the fifth force to the largest mysteries in cosmology: screening mechanisms. This is where the story of the fifth force gets almost magical. Remember the great disconnect we discussed earlier? On cosmic scales, the universe behaves as if dark energy and dark matter are shaping its evolution. But in our solar system, everything obeys standard physics perfectly. How can both things be true? If a fifth force exists and is responsible for dark energy like effects on large scales, why do we not see it in our own neighborhood? The answer, according to several theoretical frameworks, is that the fifth force has a built-in camouflage system. It hides itself in dense environments. There are several specific models for how this works, and each one is remarkable in its own way. The first and most famous is the chameleon field. This model was proposed by Justin Cowrie and Amanda Weltman in 2004. And the name is perfectly chosen. Just as a chameleon changes its color to blend in with its surroundings, the chameleon field changes its mass to match the density of its environment. Here is how it works. The chameleon is a scalar field that pervades all of space. In empty regions, far from any concentration of matter, the field has a very small effective mass. A small mass means a long-range force. So in the voids between galaxies, the chameleon field would produce a long-range fifth force that could act over megaparsecs, affecting the motion of galaxy clusters and the expansion of the universe. This is where it could produce dark energy-like effects. But in dense environments, like the interior of a star, or a planet, or a laboratory on Earth, the field becomes very massive. A massive field has a very short range force. The range becomes so short that the fifth force essentially disappears. It is screened. This is why we do not detect it in laboratory experiments or in solar system observations. The very presence of matter causes the force to collapse into a short-range interaction that our instruments cannot see. The mathematical details are elegant. The effective mass of the chameleon field depends on the local matter density through a coupling term in its potential energy function. In low-density regions, the potential has a shape that gives the field a small mass and a slowly varying profile. In high-density regions, the potential changes shape, giving the field a large mass and confining it to a narrow shell near the surface of objects. This thin shell effect means that only a thin outer layer of a massive object contributes to the fifth force, while the interior is completely screened. For objects like the Earth or the Sun, the shell is so thin relative to the total mass that the fifth force is suppressed by many orders of magnitude. This is a beautiful idea because it explains a deep puzzle. Why can we see evidence for dark energy on cosmological scales, but not in our laboratories? Because the fifth force responsible for dark energy is a chameleon, hiding in plain sight, suppressed by the very matter we use to search for it. It is like trying to find a spy who is trained to disappear whenever you look directly at them. But chameleon screening also makes specific testable predictions. In carefully designed laboratory experiments using vacuum chambers to reduce the ambient matter density, the chameleon field should emerge from screening and produce measurable effects. Experiments like microscope in space, where the gravitational environment is different, can probe different aspects of chameleon phenomenology. And chameleon models predict specific signatures in atomic physics experiments, astrophysical observations, and cosmological surveys that are currently being searched for. The second type of screening is called the Van Stein mechanism, named after the Russian physicist Arkady van Stein. This mechanism works differently from the chameleon. Instead of the field itself changing mass, the force around a massive object is suppressed by nonlinear effects in the field equations. Near a massive object like the Sun, the equations governing the scalar field become highly nonlinear, and this nonlinearity causes the fifth force to be vastly weaker than it would be in linear theory. There is a characteristic distance called the Weinstein radius, beyond which the fifth force recovers its full strength. For the Sun, the Weinstein radius extends approximately 400 light-years. This means that the fifth force would be heavily suppressed throughout the entire solar system and even far beyond it. Only at distances of hundreds of light-years from any star would the force reach its full power. This naturally explains why solar system tests of gravity find no deviations. We are deep within the Sun's Weinstein radius. The Weinstein mechanism arises naturally in several theoretical frameworks, including massive gravity theories, Galilean models, and certain string theory-inspired scenarios. It makes specific predictions for how the fifth force should recover at large distances, predictions that can in principle be tested through observations of galaxies, galaxy clusters, and the cosmic microwave background. The third type of screening is the symmetron mechanism, In symmetron models, the scalar field undergoes a phase transition depending on the local matter density. In high-density environments, the field sits at zero, and there is no fifth force. In low-density environments, the field acquires a non-zero value through spontaneous symmetry breaking, similar to how the Higgs field gives mass to particles. This non-zero value generates a fifth force. The transition between the screened and unscreened regimes is sharp, like the transition between ice and liquid water. There is a critical density below which the fifth force turns on, and above which it is completely absent. This makes the symmetron phenomenologically distinct from the chameleon and the Weinstein mechanism, with different predictions for different experiments. The fourth model worth discussing is the dilaton, which arises naturally in string theory and models with extra dimensions. In string theory, the dilaton is a scalar field that controls the strength of all interactions. If the dilaton has a potential energy that depends on the ambient matter density, it can produce a fifth force that is screened in dense environments, similar to the chameleon but with different mathematical structure and different observable predictions. Each of these screening mechanisms, chameleon, Weinstein, symmetron, and dilaton, represents a specific theoretical prediction for how a fifth force could exist and yet remain hidden from our experiments. They are not just mathematical games. They make concrete predictions that current and future experiments are designed to test. The fact that so many different theoretical frameworks independently predict screening mechanisms suggests that this concept may be pointing at something real about how nature works at its deepest level. Now, it is critically important that we examine the case against the fifth force with the same rigor that we applied to the case for it. Science is not about believing, it is about testing. And the skeptics have powerful arguments. The most serious concern involves the track record of the Atomiki Research Group. While Krasznahorkai is a respected nuclear physicist, his group has a history that gives the physics community pause. Prior to the X-17 claim, the group had reported other anomalous signals that were later retracted or abandoned. Notably, they claimed evidence for other new particles in earlier publications, but later withdrew these claims without providing a clear explanation for what caused the initial false signals. When a group has a history of extraordinary claims that do not hold up, it is natural and appropriate to apply extra scrutiny to their subsequent claims. This does not mean the X-17 is wrong. A scientist can have false starts and still make a genuine discovery. But it does mean that independent confirmation is not just desirable, but absolutely essential. And this is where the MEG-2 result hits hard. MEG-2 performed the most direct and rigorous independent test of the Atomiki beryllium-8 observation, and they found no signal. Their exclusion at 94% confidence level is strong, though just below the conventional threshold.